Okay, let's take a look at an optimization problem. Optimization problem is an application of the derivative, and what we're going to do is we're usually looking to either find the minimal value, or in most cases we're trying to maximize something. We might want to maximize the area of something, or find the minimum cost in an economics problem, something of that nature. But it's all having to do with taking the derivative. So here we're given a simple problem. Find two numbers whose sum is 20 and whose product is as large as possible. So the two things we're talking about here are the sum and the product. And the problem usually tells you which one you're trying to maximize. So since it says you want the product as large as possible, this is the one that we're going to actually take the derivative of. Okay, so starting off with this first statement, whose sum is 20. So 20 is equal to two numbers. Just choose x and y, I suppose. So x plus y equals 20. And the product, we'll just call it p, is equal to x times y. And we're trying to maximize this p. So right now, if we take the derivative with respect to x or y, we have two variables. So our goal is always to rewrite the problem in terms of one variable. I suppose that the easiest way to solve this one is to rewrite the sum equation here and say that 20 minus x is equal to y. So now what we can do then is we can put this in terms of x only. So the product is equal to x times y, and we'll just simply say that that's 20 minus x. So we can go ahead and distribute this x if we like, and we have 20x minus x squared. And now let's take the derivative. So dp with respect to x is equal to 20 minus 2x. Well, now what we're going to look at is we're going to find the critical points, or the critical values of this first derivative. So we're going to set it equal to 0 and solve for x. And doing that, we get 2x is equal to 20, and so x equals 10. Well, just like we did with finding relative minimums and relative maximums, if we're trying to find a product that's as large as possible, we want this derivative of the product to be a relative max. Well, the only critical value that we have to look at is 10. And to the left of this, if we have, let's say, a value like 5, we have 20 minus 2 times 5 gives us what? Gives us 10, right? That's clearly positive, so we're going to indicate that the function is increasing here. And then when we get to the right of 10, pick a number like, say, 15, you'd have 20 minus 2 times 15, and you get 20 minus 30 is equal to a negative 10. So all we really care about is the sign of this, and we see that it's negative. So this indicates that at x, when x equals 10, that's going to give us our maximum point. So all we have to do is go back and maybe figure out what the product would actually be. So if x equals 10, to figure out the y value, of course, this is an easy one. Subtract 10 off and you get that y equals to 10. Alright, so go back to the product, and of course we know that the product of this would be 10 times 10. So the maximum product that satisfies this equation is 100. Alright, so basically to sum it up, we usually come up with two equations. Here we had a sum equation and a product equation. We decided which one of these two equations are we trying to maximize, and that's the one we're going to take the derivative of. And then we rewrite the problem so that it's only in terms of one variable, and then we just solve. Once we solve, we find the critical points and do a sign chart analysis on it, and then we're pretty much done at that point. Alright, well, we'll try a little more challenging example next. So come back again in a minute.